In mathematical modeling, a system's microscale behavior often looks nothing like its macroscale behavior. Local complexity eventually resolves into a single trajectory. Polynomial functions exhibit this exact dual nature when plotted on a Cartesian plane. Near the origin, we find the root zone. Here, the polynomial creates complex shapes, peaks, valleys, and x-axis intersections. But as we scale out, that complexity disappears. Past the final root, oscillations shrink, leaving a singular path shooting toward infinity. This resulting trajectory is known mathematically as the polynomial's end behavior. While roots determine the specific coordinates of a function near the origin, the end behavior determines its absolute boundaries in space. As the variable x approaches positive or negative infinity, what specifically dictates the function's final direction? In a basic quadratic equation, the direction is easy to predict because there are very few variables competing for influence over the output. But in a high-degree polynomial, multiple terms, cubes, squares, and linear variables are all pulling the function in different directions simultaneously. A negative coefficient on a middle term might attempt to pull the graph downward, while a large positive constant pulls it upward. Eventually, the function reaches a state of unboundedness, stretching endlessly, accelerating toward the vastness of infinity without ever reaching a cap. Despite the competition between terms, the end behavior is decided entirely by one piece of the equation, the leading term. Calculating local roots requires factoring the entire equation, but predicting the infinite trajectory only requires isolating this single term. This is the standard format of a general polynomial equation, organized as a string of terms with descending powers. To see why the leading term always wins, we have to isolate it from the rest of the equation and compare their relative strengths. If we compare a degree 4 term to a degree 3 term at a small value, like x equals 10, the outputs are 10,000 and 1,000. The degree 4 term is 10 times larger, but the degree 3 term still exerts a measurable influence on the total value. Now we scale the input to 1,000 to see what happens as we approach the end zone. The degree 4 term reaches 1 trillion, while the degree 3 term only reaches 1 billion. The disparity has become massive. At these scales, the lower degree term becomes mathematically negligible. Compared to the leading term, it is essentially a rounding error. This phenomenon is known as algebraic dominance. Because of algebraic dominance, we can ignore every term after the leading term when we are assessing behavior near infinity. With the leading term isolated, determining the trajectory becomes a classification problem based on two specific variables. These variables are exponent parity, whether the highest power is even or odd, and the sign of the leading coefficient. We'll start with the top row, which represents all even-powered polynomials. An even exponent neutralizes any negative input, turning the result positive. When paired with a positive leading coefficient, this creates the standard U-shape. Both ends of the graph drive upward toward positive infinity. Since the exponent handles the input sign, the coefficient sign becomes the dictator of the final direction. If the coefficient is negative, the entire structure is forced downward. Both ends travel toward negative infinity. Even parity guarantees symmetrical end behavior. The ends will always travel in the same direction. The logic changes when the leading term has odd parity. Odd exponents preserve the negative or positive sign of the original input. In the bottom left quadrant, we see this in action with a positive coefficient. The graph starts at negative infinity, crosses the origin, and shoots up toward positive infinity. As x becomes infinitely negative, the output is preserved as negative. As x grows positive, the output remains positive. But look at what happens when an odd exponent is paired with a negative coefficient. The negative coefficient forces a complete inversion of that trajectory. The graph now starts at positive infinity and drops down toward negative infinity. This crossing action creates the opposite of the symmetry we saw with even-degree polynomials. Odd parity ensures asymmetrical behavior, where the function spans from positive to negative infinity. This completed matrix organizes every possible polynomial trajectory into a single predictive grid. It reduces the infinite variations of polynomial equations down to a set of 4 predictable outcomes. To use it, you only need a 2-step mental algorithm. First, is the highest exponent even or odd? Second, is the coefficient attached to that exponent positive or negative? These two binary questions reveal the absolute boundaries of the function. This allows us to bypass complex factoring and middle-term noise entirely when we assess a function at an infinite scale. We can test this against a complex equation like this one. We immediately filter the equation, crossing out every term except the highest power. We look at negative 4x to the 7th. The exponent is odd, and the coefficient is negative. This maps to the bottom right quadrant of our matrix. The macro shape is immediately clear. It descends from positive to negative infinity. No matter how many times the function crosses the x-axis in the root zone, its final destination is now a known quantity. This certainty is a foundational concept in limit calculus. Understanding limits is about identifying which forces dominate at the extremes of a system. By mastering algebraic dominance and exponent parity, we stop merely plotting local points and begin predicting the infinite.